Okay, this is lesson 6.3, Interpreting Sinusoidal Functions. In this lesson, we're going to look at 3 examples, and I will save the... No, we'll do all 3. We'll look at 3 examples here. We're going to take some sinusoidal functions. All of them that we will be presented with will be graphs, and we're going to interpret some characteristics off of the graph. Mainly we'll be looking at the characteristics, and then we'll extend to some characteristics that we saw in previous units. But we'll relate it all back to what the relationship actually is. So we'll take those key things like period, and we'll relate it back to what the function or what the relationship actually is in terms of if it's a Ferris wheel, height and time, for example. So let's get started. Example 1 is a Ferris wheel question. The graph below describes your height in meters above the ground where t is time elapsed in seconds, or no, in minutes, as we ride the Ferris wheel. So on this Ferris wheel, the ride starts in the middle. So from the middle, we'll be going up to the top, the peak of the Ferris wheel, and then we'll be rotating down to the bottom, back up to the top, back down to the bottom, and then back up to the middle. So on this ride of the Ferris wheel, it appears we get on in the middle, or the ride starts in the middle. So maybe we're loaded in, and then our ride starts when we're sitting in the middle of the Ferris wheel. What is the period? So for A, the period, we want to look at how long it takes to complete one cycle. So I'm going to start here at the beginning, and I'm just going to trace out one cycle. So back up, down, and then back up. So that single wave. And if we look at the single wave, it appears as if we start at 0, and we go all the way till 4. So there is a period. So in terms of units, we're in time. Time is in minutes. So the answer to A, what is the period, would be, well, 4 minutes. Very slow Ferris wheel. I suppose it could be quite massive, but it isn't. It's 14 meters tall. It's just a very slow Ferris wheel. What is the maximum height of the Ferris wheel above the ground? Well, to find the max, we just need to look at the peak. And there's our peak. It's at 14. 14's in meters. 14 meters is the maximum height. C, how high is the boarding platform above the ground if it's located at the lowest point on the Ferris wheel? The lowest point on the Ferris wheel is here, so that's our boarding platform. It appears as if it's 2 meters off the ground. So 2-meter boarding platform. So since our ride started at the middle, it appears as if we boarded and then we rotated up as they loaded more passengers. D, what's your position on the Ferris wheel at time t equals 0? We start at 8 meters. E, draw the graph illustrating this situation given that the time given that at time equals 0, you are at the bottom of the Ferris wheel. So we're going to regraph this starting at the bottom. Everything else is going to stay the same, except this time we loaded and immediately started. So let's try to graph that. And then in F, we're going to do the graph assuming we started our ride at the top. So we're going to come up with 2 graphs. G says, how fast is the Ferris wheel rotating? We're going to omit that question for now. Define our speed. Let's just do E and F. So we got to keep the same characteristics. And I know you can't see the original graph, but we'll steal the scale of the graph. And I'm going to do E here, and I'll do F here. So we'll come up with 2 graphs. First one. Second one. I want to keep the same scales. So 2, 8, 14, 2, 8, 14. These are our heights. Our times in minutes. Our times we had 4, 8, We had more, so here's 2 and 6. These are halfways. All right, and in E, we are starting at the bottom. So start at bottom. And in F, we're going to start at the top. Start at top. So if we start at the bottom, we're going to start here. We know it takes 4 minutes to do a whole rotation, so after 4 minutes, we're going to end up back here. In the middle, where would we be? Well, in the middle of the bottom and would be the top. So the top would be here at 2 seconds. So where would we be in the middle? Well, we'd be in the middle at 1 second and 3 seconds. And we know we follow that nice curve shape, so we're going to curve it. We're not just going to connect it with straight lines. The reason it's curved is because the Ferris wheel is a circle. We rotate in a circle. So we're going to rotate like this. There's our first rotation. After 8 seconds, we'll be back at the bottom. After 6 seconds, I didn't center that, we'll be back at the top. 5 and 7 is when we're back in the middle. And there we have our graph if we're starting at the bottom. Now what happens if we're starting at the top? Well, it's the exact same thing, it's just flipped upside down. So we could take this and just turn it upside down, or we can actually do it. Starting at the top, after 4 seconds we would be back at the top. After 2 seconds we'd be at the bottom. 1 second would put us in the middle. 3 seconds would be in the middle, and we can connect. For our second cycle, 8 seconds we'd be back at the top. 6 seconds we'd be in the middle. 5 seconds and 7 seconds. And we can connect. Oh, pen jumped. And there we have it. Same scales, same graphs, just different starting points. All right, let's flip it over. Example 2, tides. The graph below shows the height of the tides at Prince Rupert, British Columbia for a day in September 1999. The heights are in meters and the times are in hours. Calculate the increase in height of water between low tide and high tide. So what is this characteristic? Well, this would be like double the amplitude, I guess. So increase in the height below low tide and high tide. Well, where's low tide? Low tide would be right here. And that would be at about 3, and we're in meters. 3 meters, that's low. High would be 30. So the difference between 30 and 3. So A, let's say high minus low would be 30 meters minus 3 meters. So the difference is 27 meters. So that would be like double the amplitude. Because remember, the amplitude's from the middle to the max or the middle to the min. If you put 2 amplitudes together, that'd be like a double amplitude. B, how many hours are required for 1 complete cycle of the tides? Well, starting at 0 hours, we're at high tide, so it's just the next time we're at high tide. Next time we're at high tide is right here. Here's our 2 high tides. So 1 complete cycle would be from high tide to high tide, which is 0 to 12. Now, we don't need to go high tide to high tide. You could go low tide to low tide, and that would be from 6 to 18, which is also 12 hours. So it's up to you where you look to find your cycle. But between high tide and high tide, low tide and low tide is a good spot to look. If you look between like axis and axis, like middles, you only get half a rotation unless you go to the next time we're at the same position, which would be over here. So that would be from, oh, what is that, 3? Yeah, 3 to 9 would be 6 hours, so we'd have to go 3 to 15, which would be 12 hours. So as long as you're picking points that are in the same position, you'll get the cycle. All right, last example, example 3. There's a lot of space for 2 questions. Particle motion. A scientist records the motion of a particle. A graph of that motion is shown below. We've got d distance, t times. What is the period of one complete cycle? We don't have any units here, I don't think. So let's say time is in, well, let's just keep it unitless. It didn't tell us the units, we'll keep it unitless. What's the period of one complete cycle? Well, again, we can go max to max or min to min. I think it's easy. We started at the max, let's just go to the max. So one cycle would be 0 to 4. So we got 4 units. What's the range of this function? Cool. The range would be the change in y's, or the all the possible different y values. So it would be between the max and the min, which is 3 is the max and -1 is the min. We never go above 3, we never go below -1, so that's going to be our range. We're talking about d, so we're not going to use y to say the range, we're going to use d. So let's give it a shot. D belongs to, since we're connected with a curve, it's real numbers, such that, well, this time we have a minimum and a maximum. So the easiest way to set up our range is to set it up like this. Because as it reads from D to the left, you'd say D is greater than or equal to a certain number, and D is less than or equal to a certain number. The smaller number goes first, the bigger number goes last. Smallest number is -1, so we've got to be bigger than -1 or equal to, and we've got to be less than or equal to 3. So there's our range. C says, if the particle can survive for 20 complete cycles before deteriorating, determine the domain of the function. Okay, 20 complete cycles. So 20 cycles would equal 4 units per cycle times 20 cycles would mean our graph can go for 80 units. Our graph starts at time 0, so we go from 0 to 80. So we need to write a domain between 0 and 80, and we're talking about t, so we're going to use the letter t. So we got t's belong to real, because time is any real, because we're curved, any real number, such that we have a minimum t and a maximum t. The maximum t we just figured out was 80, and the minimum t is 0, because our graph started at 0. So here's your 80-second window for that particle. All right, that's it for 6.3. Thanks for watching. I'll see you next time.